Hello, my name is Aditya Behera, and this is my Physics 2211 Lab 5. In this lab, we will investigate the motion of a falling slinky. The forces being applied are gravity, tension, and drag, but they change depending on before or after the slinky is completely compressed. At the bottom, you can see some diagrams for both before and after the slinky has been completely compressed. In this lab, we will be using Tracker to measure actual data of the falling slinky. Then we're going to use GlowScript to create a computer model to predict the motion based on the forces applied to the falling slinky. Then we will compare the measured data and the predicted data. In this experiment, a slinky is dropped from an initial height. Initially, only the top of the slinky moves, but once it becomes completely compressed, the entire slinky falls to the ground in unison. The initial conditions are as follows. The slinky mass equals 0.218 kilograms. The initial position is 0, negative 0.005654, 0 meters. The initial velocity is completely 0. The time starts at 0 seconds, and the time ends at 8.667 seconds. The T cutoff, which is when the top of the slinky reaches the bottom of the slinky, so the slinky is completely compressed, and we switch from the bottom of the slinky not moving and the entire slinky falling in unison. That happens at 5.45 seconds. For some universal constants, G equals 9.8 meters per second squared, and I found D, which is a proportionality constant for the force of drag, to be 81.4. This is me tracking the slinky falling in Tracker. I track from the bottom of the slinky. Some things to note: the axis is centered at the bottom of the slinky before it starts moving, and I use Derek's height, which is 1.75 meters, as my ruler. These are the physics equations I'll be using. I'll be using the net force is equal to the force of gravity plus the force of the slinky plus the force of drag. The force of gravity equals negative mass times the gravity times J, where J is J hat, which is just the direction along Y. The force of the slinky is before the cutoff is just the opposite of Fg. It's an mgj, and after it's set to 0. Because once the slinky is completely compressed, there's no more tension or spring force for the slinky to exert. The force of drag equals negative d, which is the proportionality constant of drag, times the magnitude of v squared times v hat, which is just the direction of the velocity. And that is after the cutoff. Before the cutoff, since the bottom of the slinky isn't moving, that is set to 0. We'll also be using the velocity update and the position update formulas. This is my GlowScript code. As you can see, I set the ball mass, the initial position, and the initial velocity to what I said on the previous slides. The T, T max, delta T, and T cutoff are all specified there. G and D are the universal constants I mentioned. J hat is just 0, 1, 0, so it's just y in the positive. It's just a unit vector of y. As you can see, while T is less than T max, I calculate the force of gravity, and then what I do is when T is less than the cutoff, I set, using this if statement, I set the force of the slinky equal to the negative of force of gravity, and I set the force of drag equal to 0. Then, after the cutoff, I set the force of the slinky equal to 0, and then I calculate the force of drag, as I said before. Then, I add them all up to get the net force, and I use the velocity update and position update formulas to update the velocity and position, and then I advance the clock. And this is just my GlowScript code running and generating some predictions. As you can see, the predictions match pretty closely to the measured values. The bottom of the slinky stays still initially because Fg and Fs cancel each other out, but once the slinky is completely compressed and there's no more Fs to speak of, it starts falling, and Fd starts actually working in the direction opposite to velocity. There are some errors in this, but I think the errors can be easily explained by inaccurate measurements in Tracker. They can also be explained by inaccuracies in the guess and check method to determine the value of the proportionality constant of drag d.